Today's segment is called Language and Robots. And to help set the stage and dive into all of the different ways that this topic is really shaping the future of robotics, I have three esteemed panelists with us. I'll have them each introduce themselves, starting with Henny. Henny, please tell me a little bit about what you do for Carnegie Mellon University.
Hi, Steph. My name is Henny Admoni. I'm an associate professor in the Robotics Institute at Carnegie Mellon. That means that I do research in robotics, and my specialty is in the area of human-robot interaction. So I think a lot about how we can use what we know about human beings to develop robot algorithms that make robots easier for people to use.
And Zeynep, tell me a little bit about what you do.
Hi, I'm Zeynep Temel. I'm an assistant professor at Robotics Institute at Carnegie Mellon University. I like building robots, especially the small-scale robots that I can carry around. I got a lot of inspiration from biology. So my robots are not like fully rigid or fully soft, or, this is, a bunch of different robots. Hopefully I will get to show a couple of them to you today.
Yonatan, please introduce yourselves. Tell folks what you do.
Hi, I'm Yonatan Bisk. I'm an assistant professor in the Language Technologies Institute. And so I work on language understanding, but I specifically come at this question of where does meaning come from? And I think that having a robot, in other words, in a body in the world, is necessary to learning meaning, which is necessary to learning language. And so it's how do we connect that abstract thought all the way down to actions in the world.
How did you get your start in this field?
By not being in this field. I started actually with a slightly different question, which was, I was thinking about how children learn language. And I thought, well, children have access to two different signals. They have meaning. So, for example, their parent tells them, oh, look at this thing. But then they also just hear us talking. And there was this question as to how much do you learn from just overhearing and how much do you learn via that direct instruction? And so I started in a field called grammar induction, which was basically linguistic grammars and to what extent can you figure out the syntax of a language automatically just by sort of overhearing it. And I kind of got to a point where I was happy with that, but I felt like we were missing that second half. And so then robotics became the way that we do that second half, where we get that sort of grounding of words into the actual world.
Henny, this actually sets me up for a question to you. When he is talking about approaching robotics from a way that people want to speak to a robot, you are approaching robotics both from that aspect, but also from other things, gestures, things like that. Tell me a little bit about the human-robot interface in the work that you're doing.
Yeah, that's such a good question. I think that at the end of the day, every robotics application has a human involved in it somewhere. We make robots for people. We don't make robots to exist separate from people. And so I think it's really important that robots understand how to communicate and interact with people. And that communication can happen through language. Obviously, that's a very popular way of conveying information. But so much of what we communicate is not linguistically based. This is sort of emphasizing Yonatan's point that you have to be embodied to really make meaning of the world. So I got my start when I did my dissertation on nonverbal communication, and in particular, eye gaze and gestures, and how people use eye gaze and gestures to interact and make their communications smoother, and how robots can also use eye gaze and gestures back so that people understand them better.
I will come back to you, Yonatan, on that, because she said something that actually makes me want to dive a little bit deeper into what language is, the big $64,000 question, or $1 million question, to use a more current phrase.
Billion.
Right, the $1 million question. Zeynep, from the conversations with Yonatan and Henny, we're talking about the way people approach robots, but you've actually had this interesting, it's still a living bioorganic being, but your approach to robotics has actually looked into the natural world outside of perhaps humans. Tell me a little bit about your work and the inspiration behind it.
I'm very interested in how things work and how I can make things, build things. I'm a very crafty person. So I got interested in machines, probably because I used to live in an Air Force base. So, I used to see a lot of like jet planes and airplanes, and I was very interested in them. So I became a mechanical engineer, and I never thought that I would actually make robots because I know how mechanisms work. I designed them, but as soon as we put this like code, software, language, it's like, oh no, how to program them, how to control them. What if they do something that I don't understand? So it was a little bit scary for me. And I also remember saying that I will never work on something that I won't see, like that I can't see. And then I started working on micro robots. So that was quite a journey for me because, again, as Henny said, we are not building robots to just be robots. We are building robots for, do things for us and with us. And I started getting interested in medical applications and search and rescue. So how we can actually help, humans in different aspects. So that led me to smaller scale robots and different mechanisms and different robotic components and how to actually build them from scratch. And the thing is, a lot of us are big compared to a lot of other organisms, like insects, bacteria, so they actually, some fish, they can manage a lot with compared to their sizes, compared to their scales. So how can I learn from them? Not only they have great mechanical characteristics, but they can also solve a lot of problems with their tiny little brains. If you think about any insect doing multiple modes of locomotion, like flying, jumping, crawling, how can they fit that much capacity in a small body? So that's how I began.
But we live in a human-sized world. How are you creating small robots then when we are used to thinking in our scale?
Do we live in a human-sized world? We can, sure, but we also make smaller robots, like vacuum robots that are way smaller than us, right? We can also think about a lot of inspection in tiny little engines that we want to, see if something is broken, if there's a risk. We cannot really get them with our hands, so we need smaller robots. And if you think about search and rescue fields or inside our body, usually if I want to make a robot that would fit in my gut or in my veins, it cannot be me scale. It has to be way smaller. So that's basically where I'm approaching it from.
That reminds me of the Magic School Bus episode where Miss Frizzle shrinks the bus so that the class can go inside the body and understand how everything works.
Wouldn't it be amazing?
And interestingly, too, it's my understanding, Zeynep, of your research is when you go inside the body, it is better for, correct me if I'm wrong, but a small micro robot will function better next to the edge as opposed to the middle of a channel. Is that correct in terms of fluidity, movement, and moving around?
You definitely read my papers. So yes, because we will see the surface effects, we will see the wall effects coming from, and smaller scale, the ruling physics is different than the larger scale. So we don't really care about adhesion or, friction that much maybe when we are moving, but at smaller scale, the adhesion will become such an important force. Or everything will weigh less. So, that would affect our equations differently. So yes, when we come towards the edges, if we are talking about swimming micro robots, there will be a different effect. So we figured out that the middle of the channel is a good place, depending on your task, of course.
I think language is the currency of what we do. Even if it's in a visual medium, I am still processing the story through words that I have been taught. So, Yonatan, what is language and how does it apply to the field of robotics?
What a wonderfully small question. Thank you.
Welcome.
Let me just summarize the history of human and social evolution. Well, in essence, that is actually, I think, what the answer to language is. So language is the codification of concepts that we as a society feel are necessary to perpetuate generationally. And so that's like a bunch of fancy words for basically saying, if we think something is important, we name it. And so we then, what's important changes, what's important grows as societies merge. We, end up borrowing those words from other places because we didn't have that concept. And so what's kind of unique, therefore, is that we end up with these terms that are incredibly powerful, but also meaningless, right? The letters mean nothing, as is evidenced by a child sounding them out for the first time or something like this. So you have this weird tension, which is this is the medium by which we communicate. This is the medium that allows for long distance and multi-generational, through time we can read 2,000-year-old texts and we can garner knowledge from those generations. So it's the medium for doing that. And yet it's just a bunch of arbitrary symbols that themselves are meaningless until society imbues them with meaning. And so a lot of what we're seeing right now, which I think is part of where there's a lot of this interest, is, ChatGPT produces language or something like this. And so like how you sort of integrate that with this notion. And I think that what's really nice about that is it actually in some sense makes this easier. None of us, well, I shouldn't say that. Many people think it's intelligent, but you shouldn't. It's not intelligent, but it mirrors things that we think of as intelligence. And I think the place that you can see this start to break down is when it becomes personal or unique. So to what extent it can produce language that is really useful. It allows us to reference things because it's aggregated this knowledge off of the internet and produces it as text. But it doesn't have any real groundings, right? So it didn't experience those emotions. It didn't actually see those objects. It didn't do those things. And so then when you need to modify them, when you say like, oh, but actually, I, for example, maybe only have one leg. So like, I can't, those instructions don't work for me. It doesn't understand what that means because it never existed in the real world. It didn't ever do perspective taking from someone else, stuff like this. And so it's missing all of that meaning. So it's really good at those symbols and then misses all that stuff that we've inherited socially. The only other example maybe I'll use that I normally bring up, and I don't know how this will land for different people, is if you are bilingual or trilingual, you've been in a situation where someone has asked you to translate something. And when you start to translate it, you go, I'm going to give you the words, but it's not really going to capture, it's not really going to convey it. And that's because, again, the words are just a reference back to that shared experience. They're just a reference back to that cultural knowledge. And so if you didn't exist in that cultural knowledge, then the words don't quite capture it. But ChatGPT can produce a lot of words.
So then how do you bridge the gap between what you're doing and the actual application?
So slowly. No, is that so the I think that there's two ways that you can come at this. One is that you can the field of NLP is really I think at a wonderful moment for creating super useful tools for people where the bridge is that they have some resource that they just can't index into fast enough. They have a database, or all of us use Google search or something like this for this reason, right? We can't read the whole internet. It's great that something else can do that for us. But then we do the interpretation. So it's basically a knowledge discovery tool that we then do the reasoning on. And then where I come in is I'm coming at this sort of from the opposite end, which is to say, if I have this robot where at the end of the day, it needs to produce, those motors have to do something. They have to say, I want this forward velocity, I want to turn with this angle or something like this. Then that means that they have to build meaning from understanding from that interaction and then have to go through an abstraction process so that moving forward becomes making progress, becomes, like the social progress or like this abstraction where a simple concept of embodiment gets connected to an abstract disembodied concept. And so how do you build sort of the meaning representations that allow you to take what you experience in one scenario and then generalize it to other scenarios, generalize it to non-physical experiences, and up from there. And I in my lifetime, don't know, but that's the sort of progression that hopefully mirrors some of what human history has done.
Zeynep, I want to take a look at some of the robots that you built. Can you give me a show and tell and just explain sort of what your team's been working on?
So this is what we call a puzzle bot. If you can see, this is like a palm-sized cube robot. It has like wheels. There are things inside. Like if I open up another one, you can see like all the actuators, battery, and circuitry is like, tucked inside. So what they do is pretty like they're actually just normal robots just moving around. But if we think about like these kind of robots, small robots, if they're walking, like crawling, and then if they come here, how will they like cross the gap, or how will they take a step down? Like, what kind of mechanisms that we can, that we can build to make these robots more capable. So we looked at the nature. You can see two things, actually. The first example I always give is the ants. So ants, when they encounter with these like gaps, they attach to each other, to their body with their legs, and then create these enormous bridges with their bodies, so that the other ends can continue moving towards the food source, or that kind of things. The other thing that I recently discovered is the human chain. So if we see a puppy trapped in the flood, we build a human chain to rescue that puppy, right? So that is like, oh, okay, so we need to build some sort of chains with these robots so that they can actually do more challenging tasks. So we started making more of them and then started attaching them to each other. So now they can actually become, well, I can't attach them because, they never work on camera. They're camera shy. But if they are, oh my God, okay, we will start again. If I'm attaching them, then they are attached and now they can move together. So I cannot really demonstrate that with my hands, but you get the idea. So we can actually create bigger chains, and we can create mesh structures, like another robot can come and then attach towards from the side. We can adjust the rigidity like this. When the robots attach from the side, this basically becomes a block. But then this is basically like a flexible chain, so we can counter different terrains with these kind of robots. So we are hoping that these robots will actually, like, helping each other, will help us to solve bigger problems in search and rescue. So that's one thing. And then the other robot is inspired by the industrial delta robots that move in 3 dimension, like X, Y, and Z, like we call X, Y, and Z. So they have 3 degrees of freedoms, and they are widely used in industry since 1970s, since they have been designed for pick and place applications, especially where we don't want humans to touch things like food or medication. So they are used to pack things. So in my postdoc, I built a tiny little version of that. I only have the mechanism here. I don't know if you can see it. Maybe
This is like a makeup tutorial, but
Yes.
with robots.
Here. So again, like 3 arms are like the delta mechanism. So this is the only mechanism part, no actuators involved. So the actuators that we built for this were piezoelectric actuators that are super fast. So we reached very high speeds with this actuator, and we actually discovered that those high speeds are faster than human tremors, human handshakes. So what we thought about is that if we make these small robots and then pick it and then pack it inside a handheld surgical tool, we can actually compensate the surgeon's hand tremors so that the needle will be always, at the same location. So after I came here, I showed this little tiny robots to Henny and Oliver and Matt, so other colleagues. And then they're like, oh, Zeynep, why don't we use them? Because they're like so tiny and cute. Can we make fingers out of them? And I'm like, oh, guys, you're weird. But yes, we can. Why limit creativity? So we are now working on building soft hands using these Delta robots, which is right here. This is an example of the hand that we built. It is falling apart because, again, we were playing with this in so many places. I like traveling with my robots, so they're always in a box with me. So as you can see, these are again 3-link robots, and we have 4 of them, kind of mimicking our 4 fingers, and they are very soft, so you can crash them and then nothing will happen and they will come back. So with these 4 fingers, we can actually do a bunch of different motions, open a pill cap, or pulling a syringe and pushing a syringe. So these kind of actions that we would need interacting with patients. So that is basically what we are working with Henny at the moment. How can we build safe end effectors, safe manipulators to interact with humans in a safe way that are capable of doing our daily tasks? So those are some of the robots that I have around.
Those are incredible. They're very cool. And Henny, she talked about industry and she talked about manipulators, which I think is maybe what the average person, if you said think of the auto industry or something like that, thinks of. Tell me how you're taking this work with Zeynep and what you two are collaborating on.
Yeah, the auto industry has been using robots incredibly successfully for a long time. And if you ever go into factories where they work, you'll notice that there are fences around them. The robots work in cages because it's not safe for people to be around them. Robots move very fast. They move very precisely. They move for a very long time without needing a break. But they're not designed at all to exist in environments that have humans close in them. And in fact, people have gotten injured and killed because they've gotten into the robot environment in unsafe ways. So if you want a robot to help in medicine, for example, you need to design that robot to actually consider what it's like to operate around a human. And that means both physically, the robot has to be safe, and cognitively or socially, the robot has to be understandable. So what we're working on, Zeynep and I are working on together with some of our other colleagues, is that physical interaction, physical safety around people. How do we get robots that have a soft touch, that can be strong enough to open a pill bottle, but delicate enough to pick up a single pill and give it to somebody on their palm or in their mouth? And that challenge, finding that sweet spot of a robot that can do everything like that, is the research question that we're tackling. It's a big question, and that's why it's research, because we don't yet have a solution. Zeynep just showed us one of the design of the robot that we're moving forward with, because it has so many nice properties. Like, it's very dexterous, but it's still compliant and soft, so it can't hurt people.
And Henny, you're actually doing work with people who have tremendous language difficulties as a result of a medical condition like ALS or something like that. I mean, this has a very direct, real world benefit that is a magnitude easier maybe for the average person to understand, correct? Tell me a little bit about how this all comes to play in a very real world application.
Yeah, I'm very interested in assistive robotics, which is a field that designs robots for people with a variety of impairments. We can all use help from robots, but there are interesting applications for example, people who are motor impaired, maybe because of ALS or because of a spinal injury or something like that. And the robots can help give back some physical capacity that people have lost. So there actually exist robot arms today on the market that are designed for people with upper motor impairment. These robot arms attach to wheelchairs, and people would use whatever interface they use to drive the electric wheelchair to also control the robot. But the problem is driving an electric wheelchair, like the wheelchair works in essentially two dimensions, right? It works on flat ground, on a ramp, but you're not trying to move it in that extra third dimension. And you're also not trying to necessarily orient it, rotate it the way you would like an airplane, for example. And that's why driving an RC car is easier than driving an airplane, in part. So what we do, that means that the same interface that drives the wheelchair, it's easier to use to drive the wheelchair than it is to drive that robot. And so we're really interested in how do we help people drive robots with really limited interfaces so that they can get the same benefit out of robots. And that requires understanding what people are trying to do with the robot so that the robot can actually take some of its own assistive action to help. So some of the work we do is on understanding how we can use AI to get manipulators to help people by doing some of the manipulation independently. The other side of things is getting robots to do supportive actions, supportive tasks. So, for example, in a healthcare setting, if a nurse is dressing a wound, they might get all of their supplies ready ahead of time and then speak to the patient and then begin assessing and dressing a wound. Can we get a robot to do some of the tasks that aren't as human-centered or as skilled? So can we get robots to open all of the packages on all of the bandages? so that the nurse doesn't have to stand there and do that and can instead, for example, engage with the patient and answer questions. So the other side of what I do is looking not at robots doing the primary task, but robots supporting by doing these secondary tasks that help make people more efficient.
I'm going to ask all three of you this, but Henny, just to continue this conversation, you have talked about how, and forgive me for not remembering specifically the semantics of it, but I'll get us close enough, I think, where AI is beneficial in this capacity, because say you've got a robotic arm to open a pill bottle and someone's trying to use a joystick to get there. That is cumbersome and takes a long time. Where AI can come into play is in running multiple scenarios in an AI algorithm to determine what the intended outcome is, and very quickly move between uncertainties to get to the bottom of it. Explain, and this will apply to all of you, how AI is assistive in some of the research that you're doing in your ultimate goals.
Imagine you were helping a kid make crafts and you watched, your 5-year-old struggling to open the top of an Elmer's glue bottle. You, as an adult, can look at what the kid is doing, kind of gripping the top of the bottle. You can understand the context, which is that they're making crafts, so they probably want to apply glue to something. And this is they're holding a glue bottle. You can understand everything that's going around it and say, can I help you with that? And the kid doesn't have to say, I am struggling to open this glue bottle. Will you please help me, right? You can notice and understand everything that's going on around it. So we're trying to make AI do the same thing. Monitor not just the joystick action that somebody is giving, but the task that's going on around them, whether it's lunchtime and they're likely trying to cook a meal, or whether they finish lunch and they're likely trying to clean up that meal, right? This makes a difference in what kind of action you want to do. Do you want to put the pot on the stove, or do you want to put the pot away? So that's how we're trying to use AI to get a general understanding of the environment, of the context, of the human intent and the human need, so that it can take action. But to do that, the AI has to maintain many possible hypotheses and then use information that it's getting, that it's observing, to resolve those hypotheses in real time. And that's what we call uncertainty. So it maintains multiple beliefs that many things could be true, and then updates those beliefs based on what it's noticing in the world and the way the human is responding.
I went through some butterfly effect nonsense in my head while you were explaining this, right? All the outcomes to ultimately get to the one that's in front of me. Yonatan, when she's talking about, say, for an AI mechanism in a robot to say, put the pot on the counter, there's a lot of language packed in there. How does AI, this is almost like a chicken and the egg scenario. How does AI inform the work that you're doing in NLP, which is ultimately AI? Help me unpack that.
First of all, extend everything that Henny said is crucially relevant, right? It's all because if you don't understand intent, if you don't understand goals, if you don't understand mechanism, it's you don't have building blocks, right? If you don't have those building blocks, it's kind of hard to do anything. So I think assuming all of that to be true, I think the language piece on top of it comes from this notion that the same concept has to get transferred. So how do you build a representation that allows for so this is where the machine learning or AI comes in, is building that representation that theoretically allows you to understand that opening a door and opening a cabinet and opening a bottle of wine it's all the same verb, but they don't look anything alike, right? The process of opening a can of Coke and the process of opening a bottle of wine are not the same. And somehow we still use that same term because there's an abstracted concept there, which is something about the state of the world that we're trying to accomplish. It goes back to some of the goals that Henny was stating, right? There's some implicit goal there, and then there's a separate mechanism for actually executing on it. And so that's kind of this core challenge for us, is how do we build that representation that's going to allow us to transfer, that's going to allow for metaphor to be used from one domain in another domain. And in practice, that looks like a tremendous amount of data. So a lot of this right now is basically trying to get as much data as you possibly can so that you can try to look for those commonalities, look for patterns, and hope that they can sort of emerge by structuring your models appropriately to guide them towards those patterns. But that's pretty abstract. I don't know how. Yeah.
I was following, and I'm a layperson in this field, so I appreciate it. But again, it's what I will say though, while it's abstract, the more I chat with you, the more delightfully overwhelmed I am by the concept, if that makes sense. Henny, what are you most excited about in your field?
I think that AI and robotics is not magic. And I am happy that we are getting more and more people to be AI literate. Some of that is, because these major AI advances have happened recently, like, the large language model explosion. And suddenly people are seeing how this could be relevant in their everyday lives. And then are saying, wait a minute, what's actually going on? And so we're having conversations about AI. So I think I'm really excited about how people are becoming more aware of the role of AI in basically any task, but also in the limitations of AI and how we really need to create AI that operates well with people.
I want to talk to you, Yonatan, about what are you most excited about in the field, your field?
I'm most excited that you asked Henny first, so I could sit here and think for a second.
That was by design.
So I'll maybe piggyback first off of Henny's comment, which is about literacy. So I think that AI is both an old and a very young field. It's actually about the same age as, for example, like the discovery of DNA, and which I think similarly is really impactful, yet very few people know much about DNA besides something they learned in high school. And but what's different is the democratization, which is that you now have access to these models on every single device that you can start to build things with. And so we've given everybody an incredibly powerful hammer. We haven't necessarily taught everyone how to use that hammer. And so I'm both really excited about just this sort of hobbyist space and all the people that are now doing things, because in general, my attitude is the more minds that you can educate, the more minds you can give resources to, the better all of society is, right? And so there's so much more creativity that's possible. There's so much more invention that's possible if everybody has these tools and everyone can build things. But they also, as Henny's, sort of hinted at, they need to be wary of what they're building and what those consequences are. So I think literacy is probably the single biggest thing. Democratization of the technology along those lines is part of that. And I think that within the academic / industrial space in particular, that availability of tools is leading to crosstalk that has never happened before. So being able to have people from very different aspects of computer science or crossing into other disciplines, whether it's digital humanities, stuff like this, those are opportunities that didn't exist when the tools were not easy to use and were not as powerful as they are now.
Zeynep, I'm curious from you, what are you most excited about in your field?
Oof, even though I'm going last, I still don't know what. There's so many things, but I will follow up on what Yonatan said. I think I'm very excited about the whatever barriers that we have in our mind, they are now disappearing. So either it is interdisciplinary or the use cases or, name whatever you want. So for example, we always thought about here is like my perception of robots is like robots has to be like, this rigid mechanisms, looks like humans, very I have to kick the robot and it will nothing will happen. That transformer kind of robot idea is disappearing as we become more competent in material science, in electronics, in AI, in learning, right? So that we can actually build useful robots. Like we can give the AI and we can give the algorithms that Yonatan is working on an embodiment. Like we can actually make robots, even our vacuum robots, tell hey, this is the third time you are cleaning that corner, move away, right? So something that would actually work in real world. And this is all, I think, becoming more and more possible with this disappearing barriers.
In my conversations with all of the faculty at CMU, the thing that has been a core tenet is the appreciation for the creativity, passion, and drive of the students. And Zeynep, I know you and I have talked about that. Tell me a little bit about the sort of academic depth of bench that you have with these students in your program.
Honestly, I learn a lot from them at this point. Like, I pretend that I know things, but they know much more than me, and I just repeat their word and whatever they write their papers. Like, I showed you a lot of props, none of them that I built. Okay, this is I built this little thing, but these other things I did not. They're all of PhD students, master's students, undergraduate volunteering students, summer students. Without them, I wouldn't have a chance to basically work on these cool projects. So they're really leading me most of the day.
I see everyone nodding. Yonatan?
Yeah, absolute joy and privilege.
Yeah. I mean, if you take the statement that when we apply for this job, we say, this is what I'm going to work on. And then if you look and see what our students have decided that we're going to work on, and you contrast those, it becomes really clear how much our research agenda is guided by, controlled by them and their insights in terms of what they think are the major challenges. And I think this actually ties back nicely to Zeynep's comment from earlier about the lack of boundaries. I think that one of the things that happens is that we've tried things, we've failed at things, we've tried again, we've said, okay, if I fail twice, maybe I'm not going to try it a third time. But they haven't failed yet. And so they are very willing to try it again. And this time they succeed. And so it means that things that we maybe thought were doors that were closed actually weren't. And that's only something we discover because of them.
Henny, the smile on your face when we were talking about the students. Tell me a little bit about your academics and the students behind the work that you're doing in your lab.
Yeah, with apologies to Zeynep and Yonatan, I have the best students.
Here comes the tech beef we've been waiting for.
This is the fight. Each of us is one person. And despite some representations to the contrary, science does not happen with one brilliant person working alone in a room. That has never been true. We stand on the shoulders of giants. I believe that's Newton. And really, we stand among a community, and our community is the students. So I can only learn so much, and I can only absorb so much, and I can only have so many creative ideas. But by getting to work together with students who have their own interests in creativity and knowledge, and getting to bring all of that together and kind of shake it up in this little kind of culture we call university, we get to see really exciting things come out. I was also going to point out, in terms of disciplinary boundaries, that I think each of us on this podcast has a formal appointment in a different department than our primary one. So even though we're primarily employed in one department, for example, I have a courtesy appointment in the Human-Computer Interaction Institute because I do a lot of work that overlaps with that community. And I think that's true of Yonatan and Zeynep as well. So even when you look at our formal designations at CMU, we are inherently interdisciplinary.
As you said, we are better together, and someday, very soon, if not now, we will be better alongside AI-informed robots. Everyone, thank you so much for your time on the panel today.
Thank you.
Thank you.
Thank you.
Pleasure.
You've been listening to Does Compute, the podcast that examines how computer science is building useful stuff that works. Thanks so much for joining us. I'm Steph Stricklen.